There we go. So that was yesterday's example. We probably still should wait for 2 more minutes. I think we promised to restart half past. And well, now I probably want to edit this video a little bit because now we're recording empty minutes here, so still a few minutes until the official start. But we had this example yesterday. I made one differentiation mistake, and then of course it was missing solving to amplitude. And now we're going to have a quick look on those. Not well, the details are on the slides, should be already on Moodle. And we're in general having lots of things of solving extrema and related solving of roots. So the plan is that we're today having a look at numerical differentiation, also a numerical derivative, and also how to solve roots numerically. And actually, I'll still, in preparation, I'll have MATLAB on, and I'll also show you how to do those in Excel. So I hope everyone's seen Excel or some other spreadsheet program, but usually these days it's Excel. Before, not sure how many of you have programmed, but I'll also show the algorithm because it's actually, when you can read code, it's a lot more simple to do in code than in Excel. And it's now half past, so let's have a quick browse through of this example here. So one key weakness on this formula compared to reality is if you're having really beefy strings and small masses, then this example assumes all the mass is on the end of the spring. So it's not exactly correct for physical, but when we're having relatively light springs and heavy masses, it gets close enough. Well, on this case, we're already specifying harmonic oscillation, which means that the amplitude does not go down. And so we know that it will be of a complex solution, so that we get those cosine and sine repeating waveforms there. And if we had this exponential term there, then it could be either depending on the constants, either actually widening or so amplifying, or it could be dampened vibration. So we solve that and find the amplitude, frequency, and oscillation period. So one reason is for the force direction is of course that when there's a minus, then when k is positive, then the resisting force is pointing at a different direction than our supporting force. But also we're going to get a positive sign on the formula here. So this was something that was a bit hard to think about which way it went, but yes, when it's written this way, we're always getting positive signs for k, and of course we're getting a positive sign for n. So k over n, which is in there, is always having a positive sign. And this omega actually stands for angular velocity here. And that's relatively clear to see when we start getting solutions, because it will end up showing there as well on the solution. So we get it as a multiplier of the t in cosine and sine. Okay, we had a formula for that. It's 0 because b is here 0. So we get the solution we had on last slide, but with some reasoning why it is like that. So let's solve the first initial condition. Put 0 on t on this formula. We get a equals -6, because sine 0 is 0. Welcome. And second initial condition requires us to differentiate. Divide and conquer, so I'm not going to do this all at once. Let's do it in parts, and also take the constant a out. So we get that kind of formula. Well, that goes to 0 when t is 0. Then the second part, well, different derivative of sine is cosine again, b omega cosine omega t. Spring constant and mass are positive, so that's why we need to only consider the positive part of omega, and omega also, by what it stands physically here, must be positive. It's the angular speed, so that way we'll still have cosine 0 here, but 4 times b is 32, so b is 8. And then we can collect the terms to the solution. And now when we try to find the minimum and maxima, we can solve the derivative of this. That is, we find the root of the derivative and check which one of those. Well, actually, it's a harmonic oscillator, so all of those with derivative zeros will be minima or maxima, and the amplitude will be the same for the example. Period and frequency, we have definitions. So 2 pi over omega is the period, and frequency is omega over 2 pi. So the reciprocal of the period. Amplitude solution. So we have now what happens here. We're taking the common term of 8 times 3 sine 4t and so on. So 8 will never go to 0. So that is 0 when this 3 sine 4t plus 4 cosine 4t is 0. Okay. Let's divide everything by 4 cosine 4t. So we get 3 over 4 tangent for 4t plus 1. Move plus 1 to other side, we get 3 over 4 tangent 4t equals -1 times 4 over 3. So get tangent 4t equals -4 over 3. Take the arcus tangent and divide by 4, and we get that solution. If we put that on the formula, we do actually get -10, because it first happens to go down, but amplitude is the same, so it repeats by some interval, and so the amplitude is 10. Also, if you plug that into your calculator, you may get funny results. So our equation is this -6 cosine 4t and so on. Let's have a look on MATLAB. So I'm going to define y equals some function of t -6 times cosine 4 times t plus what did we have? 8 times 8 times sine 4t times sine of 4 times t. And now our t minimum was, I need to check the solution here. So 1/4 of 8 tan minus 4 over 3. 1/4 times 8 tan. Yeah, 8 tan minus 4 over 3. 8 tan minus 4 over 3. So we're having, okay, it's on the negative side, that's why it puts minus there, but it repeats. And now if we call y with t min, okay, this was minus 10. On some other example, I think on some of our, so this time it's actually accurate, but on our exercise problems, we have this issue that one of those problems actually the 0 isn't exactly 0 when you calculate it using a computer. So it goes to something times 10 to the power of minus 15. So that was a little correction to the previous lecture. And before we start, let's have a look at the questions. So these are the new exercises due next Wednesday. And electrics. So we're having a circuit which has in series a resistor and a coil. And now what we know that a coil causes this type of phase shift if we had AC, but we're now supplying it to 12 volts DC. And question is, if you need to use a differential equation, how does the current behave when a circuit with those values has 12 volts DC switched on T0? So before 0, it has 0 volts, no current, and then we're throw the switch, then we're having constant voltage and start to have current. And how does the current function I behave? So now this I here is a function of time. We can solve that using the theory of differential equations. So what it's going to look like, I'm going to stop sharing, but I'll now need to find it over here. Where are my markers? There they are. So for the people at home, we're having some constant u. This is nearly invisible. Let's try a different marker. The red one, maybe. So we're having a constant u, which is r times function it plus L times the derivative of a function t. If we take the time derivative, both sides is the hints, we get 0 because we're having constant voltage, and we get r I dash plus L I dash dash. And then when you start figuring out the solution and what are the effects of the colors of which variable is which, then how the system should behave is that the current, if we current approaches u equals Ri, so I at infinity should be u over R, or 12 over 5. At 0, we're not having no current, so find the constants when it behaves like this. Critical damping. Okay, we're having that kind of a typical mass dampener and a spring system, which is the basic model we have for any kind of a vibrating mechanical system. If we added here on for DC systems, if we added a capacitor, actually the formula would be the same for this kind of a RLC circuit as it would be for the mass dampener system. Effectively, so we're having a MA, which in physical notation is often marked like this. So the dot in the top of the variable means the same as, so x dot is the same as dx over dt. 2 dots is the second derivative and so on. So this stands for time derivative plus, then we're marking it with b. X is the velocity, so acceleration velocity plus kx equals 0. This is the spring mass constant equation, what we're having there. And now we know the mass and spring constant, so we know what this m is, and we know what this k is. And now your task here is to find out what should the BP for so-called critically damped system, where it definitely, if there's no damping, it will oscillate forever. Then when we're having so-called under-damped system, we're getting oscillations that do go down by some exponential curve, but mathematically speaking, oscillate forever. Of course, we're going to have friction and we're going to stop sometime. And then critically damped is when it goes to 0 smoothly. And then we're having over damping, then it actually goes too slowly for 0 because the dampener is slowing down that. Also the reason why in cars it's not good enough to have too stiff dampeners. And you can do this probably experimentally. So if you start increasing the factor B and see how the solution changes, you should be able to figure out which of those cases we had on the lecture material corresponds to critical damping, and find then a formula for the critical damping factor. The value of that should be, it isn't on the hints yet, but the value is 100 square root of 2. That's the correct answer, or the value for the answer, but also do have your reasoning why it is so. And then problem 3 should be somewhere still. Okay, that's an easy one. So find the extreme value of acceleration for this kind of a part, and do note the domain. So it's probably easier if you plot that, and it will have more than one extrema on the, it's a third degree curve, so it will probably have two extrema. Good solve those, so when you differentiate once, it will become, so that you know which derivative values go to 0, it will become a second degree equation which you can solve. So we have this basic x equals minus b plus minus b squared minus 4ac over 2a. You can use that to solve the roots of the derivative of the force, and check if they are within the if the roots that are within the domain, and check the endpoints of the domain. And by comparison, you should be able to figure out which one is the actual absolute maximum. Drawing helps, and you can also then do that table. So we should find out that we're having a force. What's the derivative of the force? For example, if the function goes like this, we know that there's a maximum here at the end, there's a minimum here, and there's a maximum here. This might be 0. Okay, this is negative derivative, this would be positive derivative. Actually, if I remember right, it does behave like that. But do note at what points those also happen. So you should, on that kind of table, you should have, this is a function of t, so you should have t, which way the function goes, and what is the derivative value. Something like this as a table. All right. So that was a little bit of an introduction to our exercises. And then a few notes on previous lecture. And now let's go on. And by the way, if someone has trouble following up this on video, the exercises are already on Moodle, so you can check those, and of course pause, or and those of you who are live, you can then ask questions at any time. I do have a sound on here, so if you unmute your mic, you should be able to talk. But let's go on with the lecture. So, okay, numerical derivatives. So what happens when I've been talking a lot about, hey, I would do this numerically if I were doing this for real. So derivatives d over dx. Definition is this. And this is the forward difference quotient in this case, assuming positive delta x. So limits numerical differentiation. So difference quotient with just a small h forms an estimate of the numerical derivative. And the smaller the step, the closer we get to the actual value. If we get too small, then we'll start getting calculation problems on most computers. Then there's also the backward. So that if we have positive h, that's the the forward one. Then if you compare to something in the past, that's the backwards version. So let's have a look at the code. Well, let's have a new function here. So we have the forward difference. So function y dash is forward difference f at some point x with step h. In this programming language, when you start a comment, which is the person with sign doing here, right after function declaration, which is on the first line, I am able to input a help text. And actually the standard form is that you repeat the function declaration here. So function y dash is fdif f x h. And parameters f function handle to a function to be derivated, x location of the derivative, h is a step size delta x. And what's the forward difference formula? Y dash is fx plus h minus fx. And let's remember to use brackets here. Well, parentheses if we're correct, and divided by h. That was simple in this case. And when I save the file name, it suggests the function name as a file name, which is a convention in MATLAB. Now we can use that. Okay, it was saved on week 2, but never mind. Let's have some function. Well, we do already have function y here, which is a function handle. So let's try diff y on tmin with step size of 0.01. Well, that was certainly yeah, of course it's here. Yeah, it's interesting that it's so large. The derivative should be close to 0 there. Oh, that's an interesting one. If we decrease that, okay, now we're getting closer to 0. Now we just put the h to be small enough. So here we can see that when it has curvature with a relatively large h, you're getting numerical errors. And if we're having a really large h, well, then it's way off. Let's try doing backwards difference. Yes, I want to create it. So that was a different way I can do a file. I just had the edit command and I used a file name which did not exist. So now it complains that just spell checking here, so it's known by a different name and fix it. So backwards difference. And okay. So we're having this as the higher value would be that way. Let's see what happens when we try to use this. So okay, all right, those are the wrong way now because we're getting negative values here, probably the wrong way. Let's see if it, yeah, it approaches 0 from the different side. So we're looking at the different side. So it approaches it from a different direction. And then what's the solution? Well, in many cases, we can use the center difference, which well, one way of thinking about that would be either yeah, let's fix that. So we're having x plus h and divided by 2h. So that would be one way of doing it, or this is equal to y dash equals backwards difference fxh and one thing missing, divided by 2. And this does converge faster, but there are some edge cases where it does give you a derivative where none actually exists. But now we can try y t min 0.1. Let's try with a crazy large value, and it already gives us a nearly 0 value here. And if we get closer, it becomes 0. So converge is significantly faster, but there are some edge cases like, for example, if we have here absolute value of x, does absolute value at 0 actually have a derivative? It doesn't, correct? What does our center difference say? Oh yeah, it says that I have a syntax error here. It says that the derivative is 0. Why? Well, on the other side it's -1. On the other side is +1. And now that we're taking the backwards and forward difference and doing the average of those, the average of -1 and +1 is 0. So this was the symmetrical difference quotient here. And yeah, I already had a suggestion how to represent functions in programs one way. We do have different programs on C, which we are going to learn. you're gonna have like that. So float function float x means that you're having a floating point number as a parameter named x, and then the function f is going to return some floating point number. MATLAB function declaration is if a f function named f has a parameter x and it returns y, it is function y equals fx. MATLAB also has these anonymous functions, so I can tell at, which is a function handle, so kind of a pointer, and then in parentheses is what's the parameter, and I just define the function. And then proper functions is what I just wrote on those files. Why are we usually using functions? Well, now that I was calling those functions, I could use shorthand here. So in this call, okay, in this case, I wrote the function here, but in most other cases, I would need to have, if I wrote long code, I would need to start writing the function here. And now I didn't need to. Function y was already defined there, ready, so I can reuse earlier code relatively easy. And then, of course, when we need to use the code several times, then we don't need to copy paste, and then notice, okay, there's a typo, and just fix the typo, fix the typo, fix the typo, and all the instances. But if you write it once and use several times, then if you need to fix it, you can correct it in one place. Yeah, for example, SD curses. So symmetric difference quotient, which is the same as our CTDiff function there. And now no need to write the function in tab because we pass the function as a handle there. And that's the short sort of tab. One use of, maybe I should at this point now show how to do that in Excel. So some function here, for example, let's grab a function from here. So we have -6 cosine 4t and 8 sine t. And so first we'll need to have the t values. So maybe 0, 0. Okay, and in Excel, remember to use the correct formulation. So in most finished installs, you need to use the comma for the decimal separator. And let's have a few of these, maybe up to. This is the boring part because I still need to drag this, but usually in Excel you don't want to drag this format. I'm going to show you relatively soon how to autofill stuff, and for that reason I'm putting some whatever over here. And we're going up, control and up, and then the function. So now we're using the t as a reference. So function declaration in Excel starts with an equal sign. We had what, 6 times cosine 4 times. And now I'm going to refer to t value. One way is writing this A2 or then just clicking that, plus 8 times sine 4 times A2. And that's the function value at that point. Now how I'm going to fill these functions there, I'm going to press Shift, press Control, and press down to go to that whatever I wrote there. And I'm going to here use the function named fill, or this feature named fill. I'm going to tell it to fill down, and we will copy the same formula down there, showing us now the function values at those points. Okay. And now we could do a forward difference. So now forward difference is x plus h, which is here. Let's have the parentheses. So x plus h minus x divided by h, which is the difference between these 2 points. And this kind of formula is what you need to do if you don't have the function, but you have only the data points. So then you can still differentiate, but you will need to use something like this. I'm going to go down here, so control and arrow down. Again, let's put some text here so it will stop there, and I'm going to do another of those fill down things. And now we do have calculations of what the derivative would be based on the forward difference method. Of course, on the very last entry, now 503 is 0. So this one here is equal to 0. So that's why it gets this jump on the result. So that's good to remember, that it is not always to be trusted. If I wrote something else here, then that would of course change, but if there's no value, then the value is equal to 0. Backwards difference is a similar algorithm, but now of course the first one is going to be bunk. So I'm going to directly start from here. So we're having this is the x minus that, and then the h is still the same, so this minus this is the step size. Do note that in our calc put this wrong way. Oh, of course, I'm using the difference there. So now I had a derivative. Let's use the correct. Yeah. Okay, not exactly the same. Again, the same tricks here. I'm going to fill down. And now we have a nice comparison how this behaves in relation to the forward and backward difference. So now the last one is correct, but the first one is not calculable. So if we would try to expand it there, we get an invalid value warning. And center difference would be this plus this divided by 2. Okay, but invalid value warning still hit there. But we can still copy the formula, and this should be more or less the accurate derivative in this case. Okay, so that's how you can do this kind of functions in Excel, and this fill down is really nice if you have lots of data in Excel, because otherwise it's gonna take you a day and a half to type all of those formulas by hand. And this is still a short data set because we're having only 500 entries. And if you, for example, measure at 1 kilohertz for a minute, you're going to get 6,000 entries in a data file. Okay, finding roots. So now we could use the accurate derivative if we know it, or in these root finding methods, some methods don't need a derivative, and some methods are okay with just having the numerical derivative. So we call this solving x for fx equals 0 is the root of f. And typical algorithm needs to have some kind of a stopping condition. Then, so we'll talk about what that is. Then brute force or step searches, bisection method, Newton methods, second method, and maybe a little bit of fixed point iteration. The fixed point one is maybe a little bit niche these days. So all algorithms are defined that what they do and when do they stop. Theoretically speaking, if we talk about algorithm theory, if it doesn't have a proper stopping condition, it's not an algorithm. But the word algorithm these days is used for quite a lot of things. So some of those, well, I guess also those do stop. So they haven't run infinitely to find what YouTube videos you might like. So it is a proper algorithm too. Usually, when we're using numerical methods, we are not guaranteed to get the exact result. So stopping condition saying is good enough, or in some cases, we might just have a limit of how many calculations we want to do and then throw our hands up and we didn't find it. And of course, if we're requiring very accurate results and don't have this kind of limit of how long the calculation can take, then user might think that our program has crashed, while in reality it's still just trying to calculate results to some arbitrary accuracy, which in some cases might be impossible using numerical methods. Common conditions, so if we have changing step size, so for example, we might want to have some kind of a downhill search. So we're trying to figure out a zero by taking steps into direction that has to where the derivative is pointing. So, or the other direction derivative pointing. So going to, well, that would be finding a minima actually. So if we're, minimization could be done in such a way that if we're having a function, something like this, I'm gonna, for a moment, stop sharing the screen. Would someone kindly, if I start showing slides, remind me that I start sharing the screen again. So, okay, derivative here is negative. So the derivative, if we would, the vector would point that way. So going the opposite way, we know that if we start from here, the minimum is actually somewhere that way. So one way would be that the higher up we are here, we're going to take larger steps, and now that we're closer, we start taking smaller steps, smaller steps, smaller steps until we find the minimum. So that is what is a variable step method. And in some cases, we might think, okay, we're now taking so small steps here that we're probably close enough to minimum and just return that value. So adaptive step size. When the improvement function value is similar, but there, so okay, we're looking for a minimum. In that case, what my example was there on the board. So now when we're not really improving in getting smaller values, then we're probably close enough, and that's good enough. In finding roots, we know that we're looking for 0, so we know already that if a root exists, it has a value of 0. So when we're inside some epsilon, so really small error, we can tell that, okay, it's probably just sideways value of the x in this case of the example is very close to the actual root and good enough. And then to get maximum iteration, say if the algorithm doesn't stop, then typically we have as a backup that if we're having having run for 10 minutes or have run for a billion iterations, then okay, this algorithm probably isn't going to stop, or if it would stop, it would have stopped already. So iterations and recursions. Iteration is that we kind of make a list of values and then go through that list of values. And we're calling the algorithms steps once and then call the algorithm again, but we are kind of like doing the algorithm once, possibly unloading values from memory and doing it again. Recursion means that the algorithm calls itself within the algorithm. And taking stoppage in iterations, typically, if we're having a for loop, which means that for some values, increase the value of each step until it reaches k, or for each type loop, which is in MATLAB, so we're having a list of values and go through those lists. Then we typically increment or check before the step that it is still valid. And then there's also the after step. While this condition is true, then keep on doing, and then after step checking that if it's still true. So a condition means, for example, while absolute value of x is greater than 1 million parts, still continue looking for the root. Okay, my internet connection sounds stable probably because I'm on the VLAN and on the VPN. Hopefully the streaming still works. In recursion, typically we're going towards the default value. So for example, recursively finding the 0 work until we're having such conditions that we can deduce what the 0 is and then start substituting back those values. And recursion, which works where call the function calls itself, and so on. We're having several copies of the function in memory, so it typically takes quite a lot of memory. Okay, step search. We're one way of doing a step search or brute force search to find the root is we have iteration number 0, assign a starting point. So algorithms need to have a starting point. And then we check if the current value of the function is a root or close enough. If done, okay, we're done. If not, we take note that we're taking a step, so we increase the step counter. And then in step search, we're moving into some direction by step h and try again. And if not, try again. So we're going with a fixed step until we find something that's close enough. If our search space is small and the function is developed, this doesn't really matter. It's really simple to implement, and we can quickly go through a large list of values. And of course, if we're looking for a root, then we might notice that if the function changes sign, so if we start from positive values and now we're going to a negative value, we know that we have gone past root, and we might, for example, want to change the search direction and half the step size, so we'll then actually going to end up being the bisection method, essentially. So bisection method, we have two numbers, a and b. If a and if b have opposite signs, it's continuous. We know by the intermediate value theorem there, which was on one of the very first lectures, that must be a root between a and b because it's continuous. And if it's continuous, all the values between if a and if b must exist between A and B. And then we can find root iterative by checking the midpoint, check which sign it is, and then replace the endpoint of the interval with that sign. And then this allows us to halve the interval, and then half and half and half until we know at what interval the root must be in. So first step was there. Second step, so now we notice that this midpoint is having a positive sign, so we replace the b equals 5 with b equals 1.5, run the step again. So now we have zoomed into the left part of the interval. Oh, it's having a negative sign, so we replace the -2 with the 0.25, and so on until we get close enough. Okay, now I'm getting connection errors on the VPN. I needed to be in the internal network to see my files apparently. Newton's method is faster. So if we know the derivative, whether numerically or then if we know it by actually derivating the part, we can estimate that if the function would be straight, then where would it hit so where does the tangent of the function hit 0? That's for linear functions, that's really easy to solve. So we solve that and assume that the function would be straight, where would it hit 0, and then check that as the next point. Common stopping criterion is that if the change in x value is under 1 billionth part, then we're close enough. So here it starts from the same function, start from 5. And what we see here is we're taking the tangent from 5, it hits at 2 point something the axis. We check the value at 2 point something. Second step, we hit the axis over here. Again, check the value, and now we're on the third step, we're already getting really close to 0. So much faster than the 3 steps we had before. Of course, we now need to calculate the derivative. So if we're doing that numerically, then for each step, we need to evaluate the function at least twice. Also, Newton's method doesn't always converge. So if we're having an S-shaped curve where the root is really close to the vertical part, it can overshoot. And if it has a kind of a local minimum type, it may end up going there. So it might overshoot like this. If this function would be slightly lower, you would probably then keep on overshooting both sides. But in the case of this example, it would probably soonish then find root from the left side. But if it had this kind of S shape on both sides, then it would potentially overshoot eternally and not find the root. Second method, similar, but instead now we don't need to differentiate. Now we just estimate the slope by using the slope. And same formula, otherwise we just use difference quotient instead of the so we directly put our hands up and say we're going to use the numerical derivative here and then use the same thing. Preferably opposite side of the root, but not necessary. Works fine. And do note, this is not the second method if we're doing kind of a midpoint estimation that way. So what we're showing here on the not the second method part is essentially using kind of a bisection method, but where the bisection is weighted by the distance from the 0. So here, second method, at which point does it hit 0? check tear, replace the interval endpoint that we have the same sign, check again. Okay, now we're going to, because sign is negative, we're going to replace the left one. So now it's going to actually head away, but then the next one will get closer. Fixed point iteration, if we can state the function in such a way that x is gx, then we can use something called fixed point iteration to solve fx is 0. So, but we need to state the fx in such a way that we have x on one side, and then the rest of it is this gx. And there is a requirement that the absolute value of the derivative of gx must be under some k, which is less than 1 on some iteration for it to converge. So how does it work? We start from that kind of function, somewhere there, check where it would be on what's the x value here, and reflect there. And then check the x value to where x matches this gx, it's there, and check the value there. Again, we have gx value, check the locus of x, and so on. It will spiral there towards gx equals x. This was, of course, a different function. We're having x equals minus e to the x as the example function here. So those were the 3 most important methods for finding roots in a numerical manner. And this concludes our lecture. First exercises today, next exercise tomorrow. I'll try to get hyperbolic functions also on tomorrow's demo lecture. So we're having theory 10 and maybe a few more demos. Any questions at this point, do ask. Also, if someone doesn't have mic at home, you can also ask in chat. I do occasionally check if anyone has said anything in chat, but if not, then I guess time to stop recording.